of their tag. Yeah, thank you.
Okay, okay, thanks. So we have 11 students registered for this class, very small class. So I like this class to be, interactive. Okay, I don't want to talk alone. Okay, please ask question. We can discuss, as we move on. So if you scroll down this class page, I posted some lecture slide. Okay, today we are going to talk about this, course introduction. Okay, this one. Okay, the first thing first, there is no textbook in this class, but we are going to use these materials as references. Okay, the first one is the book I wrote. This is about ARM programming, focusing on CortexA9. Okay, CortexA9, and we are going to use XUP, Xilinx University Program Material. XUP means you can search, you can Google search with XUP, Xilinx University Program and Xilinx. Then this one, Xilinx University Program. Then scroll it down, you can find the workshop. Okay. Those are, workshop. They used to come to Korea actually. So, the Xilinx used to come to Korea to give those lectures. But because of pandemic, I guess, they no longer come to Korea. But among these XUP material, we are going to focus on advanced the embedded system design with Zinc 7000 device. Okay, so this material. Don't worry too much about, don't worry too much about this Zinc. I'm going to talk. I'm going to explain to you in detail. And this is the book you can use as a reference for DNN accelerator, efficient processing of deep neural network. That book is this one, efficient processing of deep neural network. If you are interested, you can probably purchase this one. If you, especially your research interest is DNN accelerator. And we are going to use some, technical reference manual because we are going to use Zinc 7000. Zinc 7000 is this device. This device. The chip at the center of this board, Zinc 7000. And so this technical reference manual is this TRM, Zinc 7000 TRM is explaining the hardware detail of this device. Okay, so pretty lengthy, 1775. You don't have to read everything, only appropriate sections you need to read. Okay, and then JED board, hardware user guide, because we are going to play with this board. That is, this board is called JED-board. Okay, so on top of JED-board, Zinc 7000, this chip is mounted. Okay, so inside, so this is Zinc 7000, this chip. Okay, and inside this chip, there are two CPUs, CortexA9. This CortexA9 CPUs. That's why I put this one as a reference. So especially if you want to do some assembly programming, not high-level programming, assembly programming, then probably this one is a good reference you can use, CortexA9. Okay, I try to use very friendly and easy language to explain this CortexA9. Okay, and ARM architecture reference manual. If that book is not sufficient, then you can use this. That is like Bible, right? The Bible to play with ARM CPU. Okay, so you can think of it as this book. You can think of this book as a subset subset of this architecture reference manual. Okay, it is very lengthy, more than like 3,000 pages. Okay? And I assume you have taken those courses, computer architecture, C programming, and digital logic design as well. Okay, so I'm assuming you are familiar with Verilog HDL, right? Verilog hardware description language. Using this language, you are describing hardware, right? You are describing hardware using this language, Verilog, right? HDL. Okay, class page. Then there is no separate office hour because I know no one is going to show up, even though I said office hour. Okay, so you can ask question after this class, or you can make an appointment. Send me an email. Okay, you can appointment or just stop by my office. I usually stay in my office. Okay. Oh, not ICM. Sorry, I have to change this. My office is located in 애기능 생활관 320. 애기능 cafeteria 320. Okay. My contact information. Okay. Okay. This course name is Advanced Embedded Systems, right? And then first, what is embedded system? I'm going to ask you to read those sentences because I don't want to lose my voice. If I talk alone, I'm easily losing my voice. So I'm going to ask Sang-won, can you please?
Embedded systems. Embedded system is a special purpose computer system designed to perform one or a few dedicated functions.
Okay, what is embedded system? First, embedded system is very simple. It is still computer system, still computer. Embedded system is nothing but a computer. It is really. What is computer? From hardware perspective, computer is composed of three big components. The first one, the most important one is CPU, central processing unit, right? That is brain. It is processing, it is doing all the data processing. Okay, the brain plus memory. Memory contains what? You are storing your program, right? Your program in memory. And what is program? Program is simply what? Program is simply collection of two things. First one is instruction, machine code, right? And data. So you have instruction, data stored in memory, right? And CPU is simply reading instruction executed based on some instruction some instruction asks you to read the data and do some processing, right? So program is very simple. Program is just collection of instruction, machine code, and data. Right? CPU simply read instruction, execute it. Right? That is computer. And then a lot of I/O devices. That is computer. Right? If you have CPU memory, then that is not useful to human because it is not providing interface to external world. Right? So you have a lot of I/O devices in computer. Keyboard, mouse, Wi-Fi module, Bluetooth module, hard disk, you name it. A lot of I/O devices, right? So these three components, combining the, integrating these three components, that is computer. That is also embedded system. Embedded system is also computer, but the difference between embedded system and your computer, your desktop or notebook computer is what? Desktop, notebook computer, those are general purpose computer systems, general purpose, right? But embedded system is special purpose computer system. It is built to perform only some specific tasks. Okay, those are examples. Those are examples of embedded system. Think about this GPS navigator in a car. So, in GPS navigator, you set destination. Then the computer inside GPS navigator is finding the shortest path. So when you drive, you just follow that path, right? So computer inside this GPS is designed to show you the shortest path. That is the only purpose you added computer inside this device. So special purpose, right? Finding path, right? Shortest path. And how about the computer inside a TV? So computer inside the TV that is responding to your remote, right? You are using your remote. You are changing channels and increase or decrease volume, right? By pressing some button, remote controller, right? So that computer is built to respond to your remote. And sometimes it is showing the computer is processing some data and show you, program schedule, right? So you can scroll it up and down, then, make some, reservation. Okay, I want to watch that, 9 o'clock news, right? So that computer, the computer inside this TV is designed to do only that kind of, tasks. Special purpose, right? Special purpose computer. So, simple. Again, from hardware perspective, embedded computer, embedded system also has CPU, memory, IO devices. That's it. Very simple, right? And what do you think? Smartphone. Do you think smartphone is general purpose or special purpose? Your smartphone. Is it general purpose computer or special purpose? What do you think? I think in the past that was classified into one kind of embedded systems. But these days, I think it is getting close to general purpose. You can do almost, almost same thing you do with notebook or desktop computer, right? So anyway, let's assume it is, embedded system, a special purpose computer system. Let's take a look inside of some examples of smartphones. Okay. This one is pretty old, roughly 10 years old, Samsung Galaxy. If you open this package, then you can see this, hardware system. Okay, so this one is Exynos. It is application processor. So in smartphone world, we rarely use this terminology. Instead, we use AP, right? Application processor. The reason why I think we use this terminology is because smartphone is running many different applications, right? Many different applications. So inside this application processor, you have not only look at this CortexA9, the quad core ARM, 4 ARM CPUs, and you have memory, right? CPU and memory in one chip. Okay, so CPU, memory integrated in a single chip. Okay, so Exynos, and then you have, the other things. The other things are all I/O devices, right? Sensors, right? Proximity sensor, light sensor, gyroscope, those things. Wireless, chip, Bluetooth, all I/O devices, right? And also this one is I/O device, right? Flash. It's like hard disk. It's like hard disk in a smartphone, right? So, and how about this? Let's take a look at the block diagram of this Exynos 4412. So this is a block diagram of application processor. So you have 1, 2, 3, 4. 4 Cortex-A9 CPUs, right? Cortex-A9 CPUs and cache, main memory, right? DDR, main memory integrated. Okay. The other things are all, I/O devices, right? JTAG, DMA is not actually I/O. It is a master component. CPU is master. So you can classify hardware component into two: master device or slave device. Slave, master and slave. Master examples is CPU and DMA. Those two components are initiating transactions. Initiating transaction. What do you mean by transaction? Read transaction, write transaction. CPU, right? For example, CPU is initiating some transaction. Okay, I want to read some data. Initiating transaction. Memory is simply responding to the request, right? So memory is a slave, right? Slave. And keyboard, mouse, some IO devices like timer, UART. So those are also slaves. They are just responding, okay? They are just responding to the request. CPU is generating request and they are responding, right? Slaves, right? Slaves and master. DMA, direct memory access. That is also, one kind of a master device because it is initiating transaction, direct memory access. We are going to talk about DMA in the class. And timer, IO device, those are IO devices. Okay, UART, I2C, SPI, all IO devices. Okay, and those are, I think, those audio devices, you can call these as co-processor. Co-processor. GPU, for example, right? GPU and MPEG encoding decoding for video processing, right? So those called you can call these co-processor. Okay, it's like CPU processor, right? Helping CPU. If the work is too heavy, you can offload. CPU, it takes too much time, then you can offload video decoding work to to this coprocessor, right? So this is a Exynos application processor, a block diagram. Okay, so again, I want to emphasize embedded system, right? Embedded system, CPU, memory, IO devices. So if you go back, this application processor, this is actually complete. This alone, this chip, one chip alone is complete computer system. We call that SoC, system on chip, right? Systems on chip. Okay, SoC. Actually, this chip alone, this one chip alone is complete computer system. So here in case of smartphone, in addition to this SoC, you are adding some IO devices, a lot of IO devices to create something wonderful, right? Like smartphone. Okay, then this is more recent Exynos application processor. Okay, came out 2 years ago. Okay, this is the application processor, Samsung Exynos. See, Samsung Exynos application processor 2 years ago. So the difference. So I want to emphasize what is the difference between 10 years old Exynos and more recent 2 years old Exynos. I highlighted this. Here you have neural processing unit. Okay, NPU integrated, and that is rough the specification of neural processing unit in Exynos. This number is performance, 2 tera operations per second. So that NPU is able to do 2 tera operations per second. Every second, tera, right? What is tera? 10 to the 10 to the power of what? 12. 12, right? So what is that number in Korean? tera. 2조, right? 2조. 2조 operations per second. 1 second, right? In 1 second, it is performing 2조 operations. What kind of operation? This operation. Multiplication and accumulation. So multiplication, okay, this one, and accumulation. Accumulation is addition, right? Accumulation. You do some multiplication, do addition, right? So that is called MEC. Okay, multiplication, accumulation, MEC. And this spec says this NPU has how many? 1024 hardware multiplier and accumulator. It has 1024 MEC unit, right? So 1000, you have this hardware is doing multiplication, then some, addition. So 1 unit, you have 1000. You have 1024 MEC unit in NPU. Because if you think about convolutional neural network, CNN, right? And the main function from hardware perspective, the main function of CNN is just, MEC. You are doing a lot of multiplication and accumulation. That is why NPU has a lot of, this MEC unit. Okay, so 1024. So let's do a little, math. So 1024 MECs. Okay, then if the NPU, if NPU is running at 1 gigahertz, for example, then you can do what is 1 gigahertz? In 1 second. Okay, let me remove this. So 1 gigahertz. 1 gigahertz means this one, right? In 1 second. In 1 second, you have 1 billion. 1 billion clock pulses. 1 billion. Right? 10억 pulses. Right? 10억, right? 1 billion, 10억 pulses in 1 second. That is 1 gigahertz. So every clock cycle, this NPU, right? 1024, NPU has 1024 multiplication. So 1 gig. How many these operations in 1 second? If NPU is running at 1 gigahertz, 1 gig in 1 second, right? In 1 second, you do this many MEC operation. That is what, okay? That is 1024 tera, roughly tera operation, right? Tera operation. Oh, sorry, 1. So 1 tera operation, just, think of it as 1000, right? 1 tera operation. And multiplication, addition, these are 2 operations, right? Multiplication is 1, addition is another. So 2 operations. So multiply by 2. So then you got 2 tera, right? 2 tops, 2 tera operation per second if NPU is running at 1 gigahertz, right? And the spec says NPU is taking 5% of real estate. Okay, this real estate, right? Silicon die. Okay, that is taking 5%, and it is costing roughly $3.5. Okay, of application processor. That is one. That is the NPU rough specification. Not only Samsung Exynos, but look at this Apple Bionic chip. It has also NPU. Okay, and performance is even better, right? 5 TOPS, 5 tera operation per second, and it is taking 7% of the silicon area. Silicon, right? 7%, and the price of this NPU. Okay. Not only this high performance application processor. So if you are familiar with ARM Cortex processor, ARM Cortex has 3 families. The first one is application processor, Cortex-A. Application, Cortex-A, and second one, the mid-range processor is R, Cortex real-time processor, real-time, and M, microcontroller. And inside this application processor, you have this application, the most high performance. That is high performance. Okay, and that is very low power consuming, low performance CPU, CortexM. So in smartphone world, smartphone case, we use people use Cortex A, Cortex-A. But NPU is used not only along with Cortex-A, but Cortex-M. Look at this. ARM introduced this family, Ethos, NPU family, Ethos, and that. Okay, so this one, Kuyun, can you please?
Exynos U55, ARM's first micro NPU, launched in February 2020, designed to tightly work with a companion CortexM 32 to 256 max, configurable 0.5 TOPS with 1 GHz, weight decoder and DMA for on-the-fly weight decompression.
Okay, so little introduction of Ethos. Okay, Ethos was designed to be used with Cortex-M microcontroller. So actually, Cortex-M is used in IoT domain, Internet of Things, very light, weight microcontroller. Okay, very light, not like Cortex-A. What would be good application of IoT? So IoT devices are sometimes battery operated. It is deployed in the forest, for example, to detect wildfire. Okay, so once you deploy that hardware system, the IoT system, that's supposed to be working 1 year, for example, without power. I would say without so with only battery. Okay, so with one small battery supposed to operate for 1 year. Okay, so you deploy very small, tiny device to detect wildfire, for example. So in that case, you use Cortex-M, very small, lightweight processor, and in some application, you can, depending on application, you can integrate this the NPU. Okay, NPU, and that is a performance numbers. Okay, 0.5 TOPS with 1 gigahertz. Okay. So in this class, if you check out the schedule in the class page, in the first half of this class, we are going to play with embedded system design. Embedded system design with Vivado. Vivado is what? Vivado is where is this? Vivado is the development environment from Xilinx. So first assignment is, I posted first assignment here. Okay. First assignment is very simple. Just install the Vivado. It's Vivado. Okay, the tool. So that is the screen of Vivado. Okay, so using that CAD environment, CAD, computer aided design. Computer aided design. Okay, so using this Vivado, we are going to design some simple, embedded systems, simple computer system. Okay, so we will play with. Okay, so one example is this. Let me show you. So Vivado is providing abstraction layer. You don't have to play with nitty-gritty detail of Verilog, the connection between hardware component, for example. You don't have to worry about that. It is automating and hiding low-level detail. You don't have to worry about interconnection between, for example, ARM, CPU, and I/O devices. This interconnection, XC. We use XC in ARM case, right? So you don't have to worry about what kind of detailed signal are existing between these two. Address, data, control. You don't have to worry about that. It is providing, it is abstracting out all the details. So it is like a block diagram based hardware design tool. Okay, so going back to class schedule. So first half of this class, we are going to play with Vivado and Zinc 7000 device to design some example embedded systems. Then we are going to focus on, after midterm exam, we are going to play with DNN accelerator. The DNN, very simple, not very complex, right? Because it is class. Okay, so this slide is a rough introduction of Zinc 7000 device. This device, that device. Okay, Zinc 7000 device. So internal structure of Zinc 7000. There's Zinc 7000. You have PS, processing system, two sections, PS and PL. PS, PL. Processing system. This is the block diagram of PS, right? PS, processing system. It is, fused into the device. That means you cannot take out. It is always there. Okay? It is hard macro device. It is fused. And this is a block diagram. If you look at this, there are two Cortex A9 CPUs. Okay, Cortex A9, you have caches, L2, L1 caches, and many different I/O devices. Okay, so this PS alone is actually complete computer system. It is SoC, system on chip, because it has CPU. It doesn't have memory though. A small memory. It has small memory. You have, look at this, 200. Look at this. You have 256 kilobyte, a very small memory, internal memory. So it has CPU, memory, and IO devices. So in that sense, it is, already complete computer system SoC, system on chip. Okay, and then this yellow part is called programmable logic, PL. So here, PL, this part, this gray, right? This gray area. That is, we call that FPGA. Field Programmable Gate Array. Field Programmable Gate Array. So if you turn on Zinc device, there's nothing. At the beginning, there's nothing inside this yellow box. Okay. So using your computer, using this Vivado, you add some hardware component like this. This component, those component, and those component. Okay. So look at this. This is a PS part, processing system, PS. Okay. So this is a PS, and the rest, this component, this one, this one, this one, this one, those 1, 2, 3, 4, 5. Those 5 component goes to this yellow part. Okay, yellow part. Okay. So you are downloading. From your computer. You are going to download these five component into PL section. This PL yellow part. Okay. So that is mapped here. So PS, PL are interacting. Okay. PS and PL. That is custom hardware we put. So it is providing very nice environment. You can design hardware, then download into this FPGA part. Okay, and that is become your hardware system. So we are going to play with this Zinc. Okay, PS and PL. Any questions so far? Okay, so we're getting close to the end. Objective. This one. 지훈.
Objective: understand and design embedded systems with Zinc 7000. Understand ARM-based embedded computer systems. Design embedded systems utilizing the Xilinx hybrid FPGA device, Zinc 7000. PS configuration, custom hardware design in PL. Understand AXI, interrupt, and DMA. Hardware debugging with ILA and VIO. AI accelerator design, get familiarized with Xilinx development environment, Vivado and BTIS.
Okay, those are objectives in this course. First, understand ARM-based embedded computer system. That is actually ARM-based, right? Embedded system. You have 2 CortexA9 CPUs. And design some example embedded systems using this FPGA device, Zinc 7000 device. Okay, so PS configuration, Xe is interconnection. Interconnection protocol provided by ARM. If you go to the industry, right, Samsung, Hynix, then they are designing ARM-based, embedded system, and they use Xe interconnect to connect CPU to all I/O devices, right? So you should familiar with Xe. At least you need to know the terminology Xe. Okay, Xe is very famous, right? And interrupt mechanism, DMA, mechanism. Okay, and hardware debugging. Once you have hardware designed, then you download it to the device, right? Zinc 7000, and you run some software. Then what if something goes wrong and the system does not work? Then how would you debug your system? If the problem is hardware side, not software, then you can use you can use those other debugging module, ILA, integrated logic analyzer. I will talk in detail about this. Okay, what do you mean by logic analyzer? Very interesting and powerful, debugging mechanism to find out the bug in hardware bug, not software bug, hardware bug. Okay, then after playing with these examples, we will switch it to AI accelerator design. Okay, and that is the environment we are going to use. My student Guyun set up this DNN experiment environment. So special thanks, Guyun. Okay. So that is the environment we are going to use. This is a JED board. Okay, the same board I showed you in the second page, course introduction, and that is Zinc 7000 device. And we are going to okay here. We are going to connect this small camera. Okay, where is that? We are going to connect this camera. Okay, this camera to the board. So video input is coming in from this camera. Then that will be sent to this device. Okay, so device. Then inside, let's go back to here. Inside this yellow box, we are going to add CNN inference engine. CNN inference engine, right? So CNN, that is probably you haven't seen. You have seen this CNN, the model a lot, right? So you are taking this one as an input, then convolution operations, then what? Fully connected, right? So using this convolution operations, you want to extract features, right? Feature extraction, 2 stages, right? Feature extraction, then classification. Okay, feature extraction, classification, 2 big steps, right? So using convolution operation, you are extracting feature. What is so special? Okay, so you have some round here, feature, right? So we have some straight line at this point, those features. Based on that features, you classify, okay, that is number 4, okay, classification, 0 to 9, classification. So we are going to put this hardware engine into PL section, and then output will be displayed through this monitor connection. So Guyun, my student, right? Guyun here, right? Guyun, Guyun, my student, set up this experiment environment. So we are going to use that and play with that. Okay. Okay. So grading policy. There is only one exam, which is taking 40%, and I'm thinking of class project. I don't have concrete idea about this class project. What kind of project I'm asking you to do, right? Probably you can propose. But my hope is project should be related to DNN accelerator. That is my hope, right? DNN accelerator. And there will be several assignments, okay, 20%, and there are, I guess, 3 presentations for you guys, for each and every one of you. Okay, each one of you have to do 3 presentations. If you look at the schedule, the first presentation, I'm going to ask you to read some technical reference manual of DMA. Okay, how DMA is operating. I'm going to give you data sheet and DMA. Then you have to read and understand, okay, the DMA mechanism and present. Okay, that is the first one. That would be. And second presentation is about paper DNN accelerator paper presentation. Okay, I'm going to recommend some papers. I already posted here. There are survey papers from MIT. We can click on this. That is a survey paper. So that paper has a lot of citations actually. So you have, so those are, examples they used to write this survey paper. Okay, those are each, dot. Each dot is one paper. Each dot is TPU Edge, Iris. Those are each, the paper. So if you go back, then they, have a lot of references. So probably you can select one paper out of this, then, to give presentation. So that is the second one. Second one, the last one is class project presentation. Class project presentation. So 3. Okay, April, if you are absent more than 3 times, don't have to show up. Okay, and 2 late show ups will be counted as 1 absence. So please don't be late. The system is recording your entry and exit, right? So please don't be late. Okay, that is everything I have for today. Any questions? Please don't be shy. A small class, turn on your microphone and ask questions. You can chat. It will be interesting or very difficult. What do you think? Jian, what do you think?
I think it's very interesting.
Okay. Unjong, what do you think? Any question?
No, I think very interested, but a little bit hard.
I don't know. It depends. So yeah, actually, it really depends. But the thing is, this class is very industry-oriented class, lab-based and very practical class. So if you go to Samsung after graduation, SK Hynix, LG, they use this Xilinx development environment, the Vivado, right? Vitis, right? So once you get familiar with this environment and play with this real chip, that will help you a lot actually after graduation. Okay, this is real stuff, not theory, right? Real stuff. Okay. And sometimes I told you, right? Vivado is doing a lot of abstraction like this, right? It is block diagram based, and it is connecting these different components automatically for you. You don't have to manually connect from here to there. It is doing a lot of connection, automatic connection. Sometimes it is good, sometimes it is bad. Okay, it is bad because in a sense that you don't know what's going on, right? Because it is abstracting out, right? So personally, I prefer to design everything myself, right? Actually, so I want to design this block myself and make connections myself. Then I know what's going on because I know all the nitty-gritty details, right? But system is doing make connection, a lot of automations. Then low-level details are hidden. So something goes wrong, then you don't know what's going on, right? That is bad part, right? If it works fine, then it's great, right? It takes just 1 minute to design this hardware system. It takes 1 minute really, because everything is automated. But something goes wrong, there's no clue. If you are not experienced, right? That is hard part. But I'll do my best to explain what's going on. Okay, what's going on behind the scene, right? Under the hood. Okay, even though it is doing abstraction. Okay, Mingyu, any comment, question?
Um, no, I have no question and
Okay.
yeah.
Sungun, what do you think?
Actually, I'm studying in MPU programming, so
Oh,
I'm it'll be very interesting.
NPU programming?
Yeah,
You do that?
I'm working. I'm currently studying Samsung Galaxy S21 MPU thermal management.
Oh, okay. Probably you can give presentations on that. That will be very interesting. Okay.
I'm just starting maybe 1 month.
Okay. Yeah. Yeah. That's okay, right? That's okay probably. So after midterm exam, probably you can give the presentation of your research, right? Instead of solving one research paper, right?
Okay.
Yeah. If it is prepared, okay. I'm not pushing you. Okay. If it is prepared.
Okay.
Okay. Dongwon? Microphone is working? Still not working? Okay, probably not working. Okay, that's it. That's it for today. If you want to talk after class, I'll be here for 1 minute. Okay, you can ask questions if you have some concern or question. Okay. Okay, that's it. That's it for today. See you next time. 여러분 뭐 궁금한 거 있으면 지금 얘기해도 되고 샤이에서 뭐 질문을 못 했다거나 하면 stop recording.